Welcome back to CS520. In this session I want to talk about memory caches. First of all, let's just talk a moment about why there is a focus on memory caches in modern machines. It's basically because of this graph. Over time, so these are years going by along the x-axis, and we're talking about performance on the y-axis. Over time, the speed of memory and the CPU have drifted apart. In other words, the progress on CPU efficiency ramped up very steeply, and memory has been growing slowly. So the importance of keeping the CPU fed with data became more and more important. Regular speed memory just couldn't keep the CPU busy enough. So over time, computer architects introduced intermediate higher speed memories called caches to try to keep the CPU fed with instructions and data. I've flattened the CPU curve out just to show you that that's the most modern part of this phenomenon, is that increasing progress with CPU has slowed down. And that's why we're seeing nowadays in the machines that we buy, we're seeing more and more multiple CPU machines as the manufacturers try to keep increasing the processing power to us. But when we look at the individual speed of CPUs, it's pretty much flattened out. I'll come back and talk about multiple CPU systems at the very end here briefly, because it does have an impact on caching. Okay, what's the big picture? The big picture is that we're talking about part of the memory hierarchy here. We have the CPU at the top, very high speed. We have then high speed memory called cache in between, and then lower speed but lower cost memory down below. So we're talking about trying to move stuff back and forth between memory and cache in order to keep the CPU happy. And of course the key principles here are locality. Right, locality, we've talked before about temporal locality, the fact that something is used once, it's probably going to be used again soon. And then spatial locality, that if an operand memory location is referenced once, then other memory locations near it are likely to be also referenced soon. Okay. So let's look at some details, some terminology. Memory cache is organized as a sequence of sets. Each set contains lines. Each line is a block plus some control information. And each block contains contiguous bytes or words from memory. Again, why this? This again is to try to leverage spatial locality. Okay. So when we go to memory, we're not just going to get one item. We're going to get a group of contiguous items and hope that the principal spatial locality will make that pay off, that we'll use the one item we're trying to get right now, and then we'll probably use things nearby soon. Okay. So we bring blocks out of memory, contiguous bytes or words, called a block. We put it in a line in the cache, and the line has some control information, so it lets us know exactly which block is in the cache. Because again, if you go back to the picture, you know that memory is much larger than cache. So we're going to have multiple items in here mapping to the same place in the cache. So we need some control information to keep track of what's actually in the cache right now. Okay. And then we have sets that contain possibly multiple lines, and we possibly have multiple sets. Alright, I'm going to have to dig in and make those details more clear. Let's start by looking at how this works with an address. An address is going to be broken up into three pieces. So this is an address of something we're trying to reference. The lower bits are going to be an offset into the block because, again, a block contains multiple items, multiple words, let's say, and we want one particular word. So the bottom bits here are going to be the offset into the block. The middle bits are actually the index of the set. So they're going to let us select what set to look in. And then the upper bits are tag bits that we will use to distinguish one block from another when it's in the same set. Okay. Because again, we can have multiple blocks mapping to the same set, and we have to use the upper bits in order to distinguish one block from another. Okay. Well, let's think about a cache line. What control information actually do we need? Well, we probably need something like this. Right, we need a valid flag, first of all, because the cache line, we have to answer the question, is there anything in it? Is it empty? Or is there a block there even? So that's called the valid flag. Is there something valid in that cache line right now? Then we have the tag bits, which we're going to map. These are going to be the upper bits of the addresses for the words that are in the block in the line right now. So we need to have a match on those tag bits in order to be sure that the block we're looking for is actually the block in the line we're looking at. Then we got a couple other fields to take care of more advanced situations. The dirty flag is there to keep track of whether the block has been modified since it was loaded into the cache. This is used for one particular way of handling writes, which is called a write back cache. We'll talk about that just a little bit more, but we may need a flag depending on how we're doing writes to keep track of whether the block has been modified or not. We'll come back and talk about that again on a later slide. Also, we have to have some control information that helps us decide about a replacement policy, helps us implement a replacement policy. So again, the cache is full, but we need to bring something into the cache. Something has to go. We have to choose a cache line, a block to be replaced. Usually what we want to do is an approximation or maybe an exact algorithm for doing least recently used. Again, why least recently used? We would want to replace least recently used is because of temporal locality, right? The thing that has been least recently used is less likely to be used again soon. Things that have been used recently are more likely to be used. So usually what we're doing in the cache is we're trying to figure out at least an approximation of which blocks in the cache are least recently used. Okay, we'll take another look at that in just a second. Okay, here's the big picture item. The key slide here for this lecture. To keep things simple, let's assume we have 16-bit addresses. My block size is 4 bytes, so that means I have the bottom 2 bits are going to be the offset. Right. Which byte in the block am I interested in? In this case, I'm interested in the byte at offset 1 in the block. I'm assuming there's 16 sets, so I need 4 bits to distinguish the 16 sets. Those bits are, like I said, will be right in the middle here. And then all the upper bits, in this case 10 remaining bits, are my tag. So when I'm doing a memory operation, the hardware is going to choose the middle bits and use that as an index into the cache. The cache is a sequence of sets. So the first step is to use these middle bits as an index into the cache to find the right set. In this case, I'm assuming I only have one cache line per set. So I just need to look in one place. I come in here, check at level 12, check the valid bits. It says it's true, it is valid. I check the tag bits then to see if they match. And in this case, they do match. So in fact, I have a cache hit. If you think about it, there's 2 ways to have a cache miss, right? I come into the cache set that's decided by the middle bits here, and the cache line in the set is invalid. It doesn't contain anything. So that would be a miss, a cache miss. Or if it is valid, but the tag bits are different, that would also be a miss because there's something in the cache at this location, but it's not the addresses I'm looking for. It's an address with some different upper bits. Notice if it maps to the same location, the same set, the middle bits are the same. But if the tag is different, the address has to be from a different location. Okay, but in this case, I'm assuming the tag bits here are a match. And now I need to go get the byte I'm after. I'm after the byte at offset 1 in the block. If the offsets are numbered left to right here, 0, 1, 2, 3, I would be interested in getting that byte, the byte that contains the value 62 in this example. Okay, so that's really the key slide here to understand how this works, right? The middle bits select the set. The tag bits are used to find a matching line in the set, and then you go in and use the bottom bits as an offset to go get the item you want. Okay. Just make a couple notes. I think I've already said some of these things, but just to make sure that everybody's following along here. Remember, memory is much larger than the cache, so there'll be multiple blocks will map to the same set. And we use the tag to distinguish between the different blocks that map to that set. This particular example, I only had one cache line per set, so that's known as a direct mapped cache. And the idea is that the location of a block is completely predetermined. There's no flexibility. Where a block will be mapped is completely determined by those middle bits. It has to go in this set, and since there's only one cache line in that set, it has to go there. So that's what they mean by direct mapped, is that you know where a block is going to be simply by its address. There's no dynamic element to this at all. There's no lookup. There's just an index using the middle bits to the set, and that's it. So that's one end of the spectrum. It's called direct mapped. So a couple other flavors. If we vary this diagram a little bit, right? One variation is we have multiple lines per set. This is usually referred to as a set associative cache. Because now we use the middle bits to select a set, but once we get to the set, we have multiple lines there, so we have to do a search in the set to find whether there's a matching set of tag bits, because there can be multiple blocks stored in the same set because we have multiple cache lines per set. Okay, this is nice because it provides us with more flexibility when placing blocks into the cache. We can generally make better use of the cache because we have some flexibility where we're going to put things. Right, in a direct mapped cache, two blocks that have the same middle bits, the same set index bits, have to go in the same place. So only one can be in the cache at a time. But if I have a set associative cache with 2 lines per set, both of those blocks can then fit in the set. So again, set associative provides some level of flexibility. And you can push that idea all the way out. The third flavor of cache is called fully associative, where now we only have one set, right? And all of our blocks are placed in one set. So what that means is the blocks can be placed anywhere in the cache, right? So in this extreme, we have one set and presumably many lines in that set. So that means it's the most flexible. Any block can be put anywhere, but of course, nothing's free in life. So in this case, then the search for the tag can now be expensive because we've got lots of blocks all in the same location, and we have to look around for a matching tag. So there's a trade-off there between flexibility and cost and performance, perhaps. Okay, let's talk about a replacement policy. I mentioned it briefly when talking about the control information. When we're bringing a new block into the cache, and if the set that we're loading it into is full, then we need to choose a block to be replaced. Right? Again, the cache is small relative to memory. Not everything's going to fit in the cache. There's going to be times when we have to replace things. And usually what we want to do is we want to use least recently used, or an approximation of least recently used, to choose the set to be replaced. The one that's been least recently used is less likely, the least recently used block is less likely to be used again by the principle of temporal locality. So how can we track what's least recently used. Or one way is just to keep a timestamp. If you just stamp each block as it's loaded in with the time it was loaded, then we could look around and find the oldest block in the cache to be replaced. That's sort of an exact algorithm for LRU. Alternative, if that's too expensive, is to keep a flag that is set when the block is accessed, and periodically sweep through the cache and clear all those flags and all the blocks. So that you can simply replace then a block that has a flag that is clear. In other words, it hasn't been set since the last time we sweep through and cleared all the bits. So any block with a clear bit is a candidate for least recently used. You know it hasn't been recently used. You can't distinguish between competing blocks that both have clear bits, but again, this is an approximation technique. Okay, so that's one issue. Is you have to have a replacement policy. And also disk writes are another time when we have to have a decision about how we're going to handle them. First thing is to notice if we're doing a disk write and the block that we're trying to modify is not in the cache already, we actually most likely will do a memory read first. So we'll load from memory the block. Once it's loaded into the cache, then we'll modify the block in the cache. Then there's two basic strategies for how to handle writes. We do a write through, which means modify the cache and write the change to memory. The problem with this technique is, again, our whole scheme here is we're using caches to try to help memory keep up with the CPU. So we have to wait for a memory write every time there's a write and slow the CPU down. That's probably not good for efficiency, for performance. So usually what happens is there's a buffer introduced here. The writes are buffered so the CPU can start the transmit of the value to memory and then keep on processing other data. That's one strategy, says write through. Write back is the alternative, where we accumulate all the changes in the block in the cache. We don't write them back. We don't write them immediately to memory. We wait. We accumulate changes in the cache. We utilize this dirty bit I mentioned before, so that we can remember that the cache block has been changed since it was loaded from memory. And at replacement time, if that dirty bit is set, we write the block back to memory at that time. This way we can perhaps avoid doing some writes to memory, because we can accumulate multiple writes into the block and only write it back when we are replacing the block. Okay. Alright, well, let me end up with just a very brief description, though. What happens when we have multiple CPUs? What if there's multiple CPUs sharing memory, which again is the common case nowadays? What is going to happen is each CPU is going to have its own cache in order to try to keep itself busy. So we're going to have multiple caches now. We have one memory. We need a method to ensure consistency across those caches. Because you can imagine that a write that is cached and not written to memory may not be seen by a separate CPU who also has, and is possibly an old value, an old version of the value cached. So you need some way to ensure consistency across caches. So for instance, a write to a block in one cache might cause an invalidate of a copy of that block in another cache, because I've changed it now, so the value in the old cache, the value in the cache of the other processor is no longer up to date. So as a side effect of writing in one cache, you may send a message to another cache telling it to invalidate its copy. So through protocols like this, you can manipulate some level of consistency across the caches. Okay, it's an important thing to think about. Sometimes you need to understand this when you're writing multi-threaded code. And I recommend taking more advanced courses in this. We'll explore this a little bit in this course, but it's worthwhile to take an advanced course also to think more about issues of memory consistency. Okay, let's stop here.